Hello everyone, I'm Siming from Microelectronic Laboratory at University of Glasgow. So today it's my honor to share our latest cooperation work with Kiel University, Fraunhofer ISIT Germany, and also Newcastle University. The topic is regarding magnetoelectrical sensing for pico-Tesla MagnetoMyoGraphy. So we are working on the minimized magnetic system for biomedical applications. So the figure simplifies our research on implantable devices in human being and skeletal muscle. Today, my presentation will be divided into 5 parts. First of all, I will talk about our target, MagnetoMyoGraphy. Subsequently, I will present our numerical simulations and the proposed magnetic sensor and circuit design. After that, the simulation and experiment results will be compared and discussed. Finally, I will draw the conclusions and the future works. So what is MagnetoMyoGraphy? Magneto means magnetic fields, myo means muscle, graphy means measurement. So overall, it is a measurement of magnetic signals generated from muscle movements called MagnetomyoGraphy, MMG. So the assessment of muscle activity is central in movement neuroscience, diagnosis of muscle and nerve diseases, and also for the motor rehabilitation. So it's very important for nowadays society and people's health. Traditionally, the muscle activity can be recorded electrically by EMG technique called electromyography from the surface of skin using mental electrodes. To reach more accurate measurements, the current EMG are using needle recording probes. So the process is painful and need to repeat the injection for patients. So it's limited to the tiny area with poor spatial resolutions. Nowadays, the magnetic signal can be an alternative method to address the limitation of EMG. Firstly, the MMG has the same temperature resolutions as EMG signals, but can offer significantly higher spatial resolution. Secondly, the MMG does not require electrical contact during the recording, and therefore the sensor can be fully encapsulated with biocompatible materials, so that can minimize the risk of infection. So my long-term version is to revitalize the magnetic measurements for the muscle activity to replace the previous EMG methods. So here we simulate the MMG signal based on the finite elements methods in COMSOL, and also calculate in the MATLAB. As you can see, the magnitude of MMG signal depends on several parameters. The major one is the distance between the muscle fibers and the sensors. When recording the signal in the isolated muscle fiber and implant the sensor under the skin, it can change in the nanotesla range. But when we place the sensor on the skin outside of the body, it can change in the range of pico-Tesla. So that signal are extremely small. So over the past 4 decades, scientists are looking for the best candidates for the MMG measurements. Here is the process pathway. The current approaches were conducted in heavy magnetic field rooms. As you can see from this figure, the conventional methods are bulky, costly, and consume large power, and also require temperature control environments. So the key questions and technical challenges remain over the 4 decades are how to minimize a sensor without losing its sensitivity, and also how to operate sensor at room temperature without using the magnetic field rooms. Here we compare the magnetic signals produced by various sources from human body like muscle, brain, and heart, also with the state-of-the-art magnetic sensing technologies. The more details can be found in this TBLCAS paper. So today, I will present a minimized, low-cost, and room temperature magnetic sensor based on the same film technologies. It's called magnetoelectrical sensor. So the thin film magnetoelectrical sensors are micro-sized that can transform the magnetic field into the measurable polarization through the mechanical coupling between the magnetostrictive and pico-electrical materials. So as you can see, it is multi-layer structures. When apply a magnetic field along the sensor lens directions, the magnetostrictive layers will elongate along the field directions and generate a string. So this string will transfer to a stress to the piezoelectric layers, where the polarization is changes with different stress level. So therefore, there is a potential difference between the piezoelectric layers that we can measure. So here is a magnetoelectrical sensor model is created and simulated in console with two main steps. One is static and another one is harmonic. So the parameters of the console model will be exported into the cadence by using the Biomedical language, which connected both the physical and electrical model for the integrated circuit designer. So the figure C here shows the sensor response curve. So what we want is to make the sensor operated in its linear range. So that's this operation points we want to approach. So still, it's very difficult to predict how precious a sensor behavior when we apply an internal magnetic field, especially when the sensor structure compress several layers of materials. So accurate and reliable simulation techniques can help to evaluate the sensor behavior with different material combinations and geometries. So here we investigated the suitability of the 3D dimension modeling based on the finite element methods to simulate a bending mode response of cantilever ME sensors. So to resolve mechanical, magnetic, and electrical coupling fields, the magnetic stretching and the piezoelectricity were evaluated in the console. So in this work, 3 different modules, magnetic fields module, solid mechanics module, and electrical statics module were used in calculate the static deformations of the sensor. The figure shows the final ME sensor structures considering its fabrications. So in summary, the ME sensors are minimized and low cost room temperature approach. And the most important point is that it is a passive sensors, which means it can operate without using any external batteries. So that can achieve extremely low power consumption for the whole systems. So here is our simulation results. We optimize the sensor performance based on the geometries, material combinations, different lengths and thickness of layers, and so on. So the first figure shows overall sensor deformation due to the different magnitudes of magnetic fields. Then the second one is the magnetic stretching that describes the changes in the dimension of the material due to the changes of the magnetization. So it is a non-linear dependence between the magnetic fields and the mechanical stress. So the induced electrical potential are shown in the third figure. Then we sweep the magnetic fields. The final DC sensitivity is compared in the figure D with the state-of-the-art works. So due to the mechanical coupling between the piezoelectric and magnetic phase, the performance of the ME sensor could be significantly enhanced if we operate the sensor in the resonance frequency, as you can see in the figure E. So finally, in the ideal simulation environments, the AC sensitivity of the sensor should be very linear and very high. So after the simulations, we fabricated our chips in the clean rooms. So a standard design cantilever ME sensor is used the same fabrication technologies in our previous works, as you can see from the reference. So a low stress polysilicon layers, the first time as a substrate integrated into the sensors using the surface micro matching process. So here shows our fabrication process. You can find more details in our latest paper. So the cantilevers were mounted on the print circuit boards, and the top and bottom electrodes were connected manually. So the right side of figure shows the packaged and assembled devices on the test boards for the following experiments. So let's move to the sensor interface design. So here is the overview process of MMG recording. In addition to the ME sensors, the analog front-end circuit plays an important role to select useful information from the measurements MMG signals. So here shows the system function blocks. First of all, we show the equivalent circuit of sensors and amplifiers with major internal noise resources. And the output the ME sensor is sent to an ultra-low noise charge amplifier, a bandpass filter, and also the microcontrol units, which includes a 24 bits analog to digital converter. So finally, the signal are transmitted through a wireless module, and then the signal will be extracted, classified, and displayed in a live view interface on the laptop. So the sensor interface circuit was also designed and implemented in a standard CMOS technologies that can offer the on-chip signal processing, amplification, and also noise cancellation. Finally, to achieve the small size and low power consumption. So this is our current work. So after the sensor and circuit design, let's move to the experiment setup. So to reduce the background magnetic noise from the earth and surrounding equipment, the sensor characterization was performed in a shared environment. So we used an active compensation techniques to the whole systems. We used an active compensation technique in the magnetic canceling box, which also includes an area of the three square Helmholtz coil and also a digital control unit. So to provide a stable DC bias field for the sensors rather than our proposed 3D printed coil, we are using the cube magnets. Our latest work is using the integrated powder-based permanent magnets. So that can be implemented inside of the sensor chip to minimize the dimension of the whole system. So finally, here shows the measurement results. As you can see, the mirrors response are matched well with the simulation results. The sensor shows a very linear response down to 175 pico-Tesla. So that is well in the range of MMG signals from our previous modeling and experiments. So the table here is summarized the state-of-the-art sensor that has been utilized in the MMG with the detection of the limit at 1 Hertz, and also address their limitations. Compared to the previous Sparky approaches, the proposed thin film ME sensor has smaller size without losing its sensitivity, and therefore it can offer better performance in the spatial resolution. So in conclusion, in order to design these integrated systems, first of all, the modeling play a key role to validate my design, and it can be divided into two parts. The biosignal modeling to simulate the magnitude of the real MD signals, and the device modeling to evaluate the sensor behavior with different material combinations and different geometries. Secondly, is device fabrications. So we can fabricate our chips in the clean room. After that is the experiments. So my goal is to validate my design firstly in the rodent animals like the rats, and implant it in human in the future, just like this figure here. So after experiments, we can change our compact modeling based on the measurement results. So it can form a closed loop that is a minimized biosystem platform we want to achieve. So that is our proposed, for the first time, minimize the high sensitivity, low power ME systems to achieve non-invasive and room temperature detections. So thank you for your listening. Thank you.